I'll be honest with you. It is uncomfortably warm in the skybox at the corner of the level this evening. I'm Res Mason. I am recovering from a cold. I am slightly more experienced in making grilled cheese. And I am overheated because it was in the 90s outside today. There's a bit of catch-up that I owe folks from the previous episode. Quick reminder, in the previous episode, this application, which has different versions, different engines, like Naive. The core code that makes this application work belongs in something called an engine, and we now have different versions of the engine which are color-coded. And we did that. Sorry, they're not just color-coded, they also correspond with different where are they? Here we go. Different points, different milestones of the project. And those milestones more or less correspond with an improvement in performance, which is represented by this number in the bottom right. So for example, this Alive engine runs at 345 generations per second, which is pretty good, but we would like to be able to compare that maybe with the default engine, which as we can see is much faster. By the way, we might not hit the expected performance levels during this episode because not only did I neglect to upload the previous episode to YouTube, I neglected to charge the laptop that I stream from. So, it is charging. I am not expecting the machine to perform as well as it normally would. Anyway, still impressive. 4,000 generations per second in flat. The thing is, the names of these engines is not documented, right? There's no place in this project, like I could do it in GitHub, Res Mason Wireworld Player. I could list them here, which I think I did with... I think I did that in the Wireworld... Nope, I didn't. So there really isn't any documentation of the different names that we chose for these different versions of the engine. So, it made sense to not just do this trick where you can name the engine you're interested in the URL, but to also add a drop-down, which looks a little fancier than it used to. The drop-down used to be up here. At the end of the last episode, it was up here, and now it's down here next to the speedometer. Mainly because while it does involve speed, it's more about its performance and comparing the performance of these different implementations. They're in order from oldest to newest, and what I was struggling with at the end of the last episode, of the last stream, was being able to simulate the this pattern in one engine, and then just hot swap to another engine. So you'll notice the generation is still in the hundreds of thousands. It's like 100,000 at least. The digit on this handy display inside this virtual computer is at 5, whereas it usually starts at 0, right? So we know just now that we successfully swapped between the flat engine, and the neighbor's engine. And we can hot swap, boom, to the linked engine. We can swap all the way down to the naive engine, the alive engine. These are not the final colors of the different engines. I'm happy with some of these, but I don't know. I'll fiddle with those color themes at some later date. But yeah, I ended the last stream way late after the normal sign-off time because I was struggling to get this data in a format that all the different engines could agree on. And that format, you could say, oh, that format should just be, the format that comes out of the parser, because we have a parse.js, which takes things like this text version of... Sorry, one second. Here we go. Sorry, one second. For some reason, my mouse isn't properly scrolling. Tracking speed, natural. I'll have to look into it later. Here, word wrap off. That's why. It wasn't the mouse, it was the editor. Okay, so we can see in this text file, Owen more horizontal, that some of the structures that are in this pattern on screen are represented in a kind of ASCII format in this file. And the parser's job is to take this format and another format called MCL, which just happens to be a format that is used for a lot of the other example files that we have, but is a little harder to make sense of. Right? Like, what is this? It's hard to say. But it's more compressed. Regardless, the parser takes these two formats and it turns them into an array of arrays of cell states. So remember, cell states allow us to say, every cell, every pixel really, is one of four colors. There's the dead color, there's the wire color, there is the head color and the tail color. And it maps these characters in this text file to cell states. And just like this text file is a grid, right? It's like a grid of characters. The parser turns that grid of characters into a grid of cell states. And then here we are. The result is passed by the main Wireworld module into the engine. And the engine engine common initialize, here we are, gets that data and passes it into each engine's initialize function, which then, if I look at naive initialize, it grabs the width, it grabs the height, and it looks in that grid of cell states and turns it into whatever representation of data is internal to the engine. And remember, these engines are actually... Sorry, there we go. These engines are actually very different from each other on the inside. On the inside, this stores all, the naive implementation, which we started with, stores all of these pixels in a 2D grid, and computes the next generation by looking in that grid and doing a whole bunch of stuff that we now know is suboptimal. Whereas in the neighbor's engine, there's still a 2D grid, but... Or sorry, in the neighbor's engine, there's no longer a 2D grid. There's just a list of cells, and they have a list. Each cell has a list of its neighbors. So this cell that has an electron tail right now, right? Tail? Yeah. This cell that has an electron tail has a neighbor here and a neighbor here. So its list contains references to these two cells and has a length of just 2. But this cell has a list of neighbors of length 0 because it has no neighbors, right? And this cell has a neighbor list of length 3, and it contains these 3. Sorry, 4. Of length 4, because of that fourth one. Yeah. Anyway, and so the representation of the simulation in the memory of this engine, neighbors, is entirely different from naive, which is entirely different from linked and flat. And remember, linked and flat are kind of comparable. Their difference is flat gets rid of some of the weird stuff that we were relying on JavaScript to do, like modeling cells as objects and containing properties. But otherwise, these two are the same. My point is, these engines are very different on the inside. But in order for us to support them in the first place like this, we did have to change, like as we were writing them out last week in the last episode, what we ended up doing was making them all speak the same language that the renderer speaks. So the reason that we can see any of them on screen right now is because they all do two things the exact same way. They all send the renderer a list of every non-dead cell, and that list is in order. So the index into that list is a unique number for every cell. And so that tells the renderer what cells should be drawn as wire and what cells should be drawn as dead. But it also gives the renderer a lookup table of every cell to draw as a head or a tail when we tell it to. And that's the other thing that all the engines now do. They send, in the render function, they send the renderer a list of heads and a list of tails. Specifically, the indices of those heads and tails in the list of all non-dead cells that the renderer is initialized with. In other words, all the data needed to construct this image is formatted the same way across all these different engines. And to be honest, that is a much cleaner means of transferring the state from one of these engines to the other when, like in the middle of running, we do a hot swap. Boom. Right? What happens there is in the Wireworld module, in the swap engines function, Wireworld sends post message save to the engine. It tells the engine save data. And the engine comes back with save data. And as soon as it does that, we stop listening to that engine, and we repurpose our rebuild engine function to terminate that engine, stop listening to it for anything, and create a new one in its place and start listening to that. Only now, rebuild engine uses engine name to look up the web worker that corresponds with the dropdown in the UI, or with the URL. So, we rebuild the engine, and if we just left it at that, then it would reset the state of our simulation when we initialize. But instead of passing in the data we get from the parser, this time around we pass in the data that we get from the previous engine, which does contain, if we look in the engine common save function, here we are. The save data is an extension, is a copy of the original data that we parsed out. Mainly because that's the least error-prone solution, right? It's good to just have this data around. But we attach to it a save data object that contains the current generation, the current head IDs, and the current tail IDs. Except it's not the current head and tail IDs. It's the grid indices. It is the X and Y, basically. It's like it's the unique ID of the pixel that the head or tail occupies. Because again, that grid index is like the shared language between all these engines. It is the thing that we tell the renderer that, light this pixel up, light that pixel up. And then, when we initialize, if there is a save data object, then we copy it and we reproduce the head ID and tail ID lists that map those grid indices back into the IDs. And we just pass that into reset. And then reset recovers the generation from that, because that's pretty straightforward, and then passes it into the hard-coded reset, which, for naive, for instance, save data. If save, so, each engine uses that save data differently in the reset function. In naive, it basically says, oh, there's save data, then create a set of all the head IDs and all the tail IDs, find every non-dead cell, get its grid index, and then by default it's wire, and it's a head if that grid index is in the saved head IDs, and it's a tail if that's in the cell IDs by grid. This is the wrong name. Cell ID. Alive, cell grid index, this should be cell ID. And in neighbors, reset, has ID. Okay, good. Cool. Okay. I named some variables wrong in naive and alive. Okay. Let me try that again. So we make sets that we can easily look up head IDs and tail, the cell IDs in these to check for membership. We iterate in the naive, reset function over every single pixel that isn't dead, and then we get its cell ID and we look it up in the saved heads or the saved tails. And for the other engines, the result is basically the same. Let me just check that this works. Flat. Boom. And we are at 2. And then naive. 2. Good. And flat. And alive. 2. Good. Okay. Everything is working as it should. Okay. Isn't this cool? What other website lets you do this? Like, I realize there is no indication right now to a user what is going on, right? It's not obvious what this app does. You can kind of suss it out. So yes, there will be a little better UX and conveyance when I get around to it. But as an educational tool, somebody interested in how you make a simulation like this can now try these different engines, and we can talk about those engines in the help text or something, and link to their implementations, right? But they can compare them and be like, oh wow, okay, so a JavaScript algorithm to simulate this computer that, you know, iterates over every cell, but it ignores the dead cells, performs at roughly like 275 generations per second. Whereas if you represent the neighbors of every cell, so same simulation, but instead of iterating over your 9 neighbors, you just have a list of those neighbors. If you click that, boom, and now we're at 330 generations per second. So that's the sort of speed up that we can expect if we perform that optimization. If we replace the grid of cells with linked lists of cells, where all the heads from the previous generation are linked together, all the tails are linked together, and you generate the new heads from the list of heads on update. We went from 330 to 1,000 and, let's say, 1,150, 1,160, right? And then when we flatten it, and we see that we get that advancement just from walking away from the JavaScript objects, right? And going straight to an array buffer. Which, granted, I know I'm repeating myself, but flat. So, you know, the code in flat, actually the code in flat is pretty small. What's nice about this engine stuff, by the way, is engine common stores a lot of things in just 200 lines of code that are shared between all of these engines. And that allows each engine to be a much smaller, easier to comprehend chunk of code, right? By the way, another thing that I did after the stream last episode was I replaced the ECMAScript class syntax, because I was using classes to do this, which is weird, right? Because we aren't actually using classes. It was just an opportunity to do inheritance, but now I've got it based on composition instead. The engine common file creates an engine. Basically, it initializes a system inside an object. Not even in an object, just in a closure. So build engine is a closure, and you pass in the theme that you want things to look like, right? Like yellow and orange is this theme, blueprint colors is this theme. You pass in an initialize function, a reset function, an update function, and a render function. And all of the stuff that has to be done no matter what occurs outside of those functions and just calls those functions inside, right? There's reset. Calls the internal reset. Update calls the internal update. Although, hang on. Where am I calling update? Not in a lot of places. Let me just try something. 1 second. Update. Replace with generation ++ update. And these... Oopsie. Replace with that. And... generation plus equals 6, right? 1, 2, 3, 4, 5, 6. Let's just try that. I'm just curious, like, why not? Yeah, still works properly, right? I think. whatever. I'm happy with just doing this little update function. Not a problem. I mean, it does add a little bit of overhead, but I mean, the goals that we have for this project moving forward are going to make an optimization like getting rid of this no big deal. I hope. Because after I walk us through these changes from after the last stream, we are going to do some research. We are going to explore the unknown. Okay, so renamed some variables in the naive live reset implementation. Yeah, reset implementation were improperly named. Is that the only change I made? It is. Let's run the prettier. No change. Push. Okay. How's my battery? Almost 70%. Okay. Let's stop with that nonsense. So, again, this is a JavaScript project so that people can just browse to it, right? Boom. Eventually it will live at resmason.net/wireworld, which at the moment displays the 10-year-old Flash version to nobody because the Flash plugin no longer runs. And right, we're trying to make it run as fast as possible as an exploration of the performance constraints of JavaScript and web tech in general. It is impressive what we're able to accomplish with just plain old JavaScript. We have not attempted any graphics accelerator, strategy, which will come later. That's more of a kind of flight of fancy. We've just, we haven't used WebAssembly either. WebAssembly being a powerful... Here we go. A very powerful API for... whatever. A powerful API for computing things across the web at a low level without JavaScript. So that we could take things like C or Python or some other language that's not native to the web and compile it into an assembly, just like kind of like a binary executable, but that every browser can read, right? And that doesn't have the limitations of JavaScript, right? When we went from linked to flat, we shed a lot of the slower things in JavaScript. We will, at some point, try to do some WebAssembly stuff, but not tonight. Tonight is an opportunity for me to learn absolutely new things, and if you are interested, you can watch me learn them. The thing that I'm learning, is Gosper's HashLife. So this application Golly that I've shown a few times, patterns, Wireworld. You know what? Actually, I will show. Is this interesting? No. What's a good? Sorry, one moment. You know what? Might as well do HashLife. I don't know what this is. Unlimited novelty. Oops. Let's reset that, because I have no idea where we are. Okay. Ah, I bet unlimited novelty creates a region in space that is difficult for HashLife to compute. But regardless, you know, I haven't run this for very long, right? But we are already at generation 681,000, and I am way zoomed out. If I zoom in, you can see, okay, here are the cells, right? Zoomed back out, it's kind of hard to fathom just how much computation is happening right now. These pixels that we're seeing here are gliders. Are they just gliders? Pairs of gliders that are going off in this direction, right? It's actually interesting that they are going in that line, and there's other gliders that are going in this line. And there's all kinds of construction going on here. Yeah. So we are at population 2 million. This might not have seemed impressive, but this for this pattern to even be computable in that period of time is incredibly impressive. This is actually a stress test for HashLife. Let's try a different one, like Metapixel. What is this? There we go. Look at that. So what we're looking at right now is Conway's Game of Life being accelerated through HashLife to simulate Conway's Game of Life. Now the reason there's these empty gaps and then there's these weird bits is because whoever created this decided that these pixels should not be made any place where they will never be filled as an optimization. And so we are seeing a Conway's Game of Life sim running. Look at this. Sorry, this whole time I was looking at population and thinking that was the generation. It's not. This is the generation. 1.545 times 10 to the 14. 1.545 times 10 to the 14. This is leaving the existing Wireworld player in the dust. Right? Here, Metapixel. Off you go. So now we are running Gosper's life in life. And it is stepping. By the way, this step is exponential. Basically, the time scale that the simulation can advance at in HashLife has to be, well, it has to be a power of some base. And the idea is, it's hard to describe. My understanding of HashLife is basically, you model the world in a quad tree, and a quad tree is one of these gizmos. So this is all of space, right? This box encompasses all of these points as data. The points are stored in the boxes that enclose them. But it's weird, right? Because some of the boxes are small and some of the boxes are large. Well, these 4 boxes actually occupy this box, and this box, and this box, and this box, and this box actually occupy this box. And this quadrant, and this quadrant, and this quadrant, and this quadrant occupy this box. So there's a fractal. It is fractal, but that's beside the point. There's a hierarchy. Actually, this is a better image to demonstrate. There's a hierarchy of nodes, right? It's a tree of nodes where each layer represents a smaller area. And one of the reasons to do this is to simplify collision detection in a game, for example, right? If this circle, if you're interested in whether this circle and this circle collide, you can be like, well, are they in the same bounding box? Or, you know, if you measure this radius and you add them up, you can be like, are there any bounding boxes around this guy's bounding box that are close enough that they could collide? Point is, that wasn't a good description, but basically you can reduce the complexity of your model to just represent things that are proximal to each other, that are close together, right? So you don't have to have this resolution to your model in a completely empty space. So Golly's using Gosper's HashLife algorithm, and it does this. It takes not all these cells, but all of these cells, and it puts them in quad trees. Sorry, it puts them in a quad tree. But it's not just any quad tree. The nodes are cached. In other words, if, for example, it's a poor example, but if these 4 cells were in a node of the quad tree, and these 4 cells were in the node of a quad tree, then they would be represented by the same node. The parent of this node over here and the parent of this node over here would reference the same node. In other words, for Conway's game of life, there are only 2 level 1 nodes. X and O, right? Alive and dead. And let's see. 1, 2, 3, 4, 5, 6, 7, 8, and 8 level 2 nodes, which is like this. X0, 0, 0. Okay, let me do this again. X, 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 X. Yep. And then X, 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 X. Yep. And then XO, 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 XO. I think that's all of them. Are any of these the same? No, they're not. But you see what I'm getting at. And if you look at this, every X in here is just a reference to this guy. And every O in here is a reference to this guy. Now, how many level 4s are there? Well, I don't know. And some number of level 3, not level 4, level 3 nodes, such as XX. I should use a classic one. Hang on. There's one from the Dr. Dobbs. Just gonna transcribe it because I wanna at least understand how my knowledge of this expands over time. There we go. Okay, so x x x x x x x. Is it just that? Yes. Okay. So if we look at this guy, OXXO, is not up here. Hang on. X X X X O O O O X X O O X X O O X X X X. Okay, that's the one that I got wrong. Okay. 1 second. You know, I'm gonna do these all over again. Oh. Thanks for your patience. Okay, the first one, I'm gonna have half of it be x, the first half be x, and the second half be o. The second one is gonna be the first half of that is x, and then the second half is o, and the first half of this is x, and the second half is o. Okay, now this one is gonna be x, o, let's see. X X O O X X O O. There's 16, aren't there? Obliterate this again. X O O O O. Oh, oh, it's magic, and that's all I can probably sing. I'm making this hard for myself. Let's do this. X, O. X, O. X, O. And then lastly, everything to the left of this gets an X up top. Okay, so now I should have all of them. And that makes sense. This number, 16, should be 2 to the 4. Right? On-off times on-off times on-off times on-off. 2 times 2 times 2 times 2 equals 16. Anyway, the point I was trying to make down here is here's like an arbitrary pattern, right? And it's got, as this Dr. Dobbs article from 2006 illustrates, the quad tree has a northwest, a northeast, a southwest, and a southeast node that is half the size. And these correspond with some of these, right? OXXO, OXXO, there we go. And then OOXO, OOXO. Down here, XOOX, XOOX, and then another OXXO. And so this node and this node are actually the same. And they literally are the same. This illustration makes it look like it branches, but actually, you just wind up, here we go, you just wind up mapping all of the shared nodes together like this. So the quad tree is hierarchical, but the actual nodes that you're using don't have to be, right? So we're actually going to call this 1, 0, x, o, and then this is going to be called A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. And this guy is actually... Can't select out here. 1 second. 2D typing is a little awkward sometimes. Okay. So this guy, OXXO, OXXO is J. Same down here, J. Right? We don't even need to contain these, right? And then OOXO, OOXO, that is N. And then XOOX was over here, and that's G. Right? In other words, the quad tree to the left has the nodes to the right that are in this list, just as these nodes have these nodes in this list. Ugh. So what good is this? What's cool about this is, because the neighborhood in Conway's... Excuse me. I'm sorry. Because the neighborhood in Conway's Game of Life is a 3x3 grid, every 2 to the... Well, every 4x4 grid can store the 2x2 future of its center. In other words, if we do this, sorry, these actually should be 0, and these should be 1. There we go. Yeah. You get the idea. So, this raw value, let me make it a glider, actually. So, 1, 1, 1, whoops, 1, 1, 1, like that. So this is a Conway glider. So first of all, 0101, which is OXOX, is K. 0001 is O. And then down here, 0100 0100 is L, and then down here 1000 100 is H. There we go. So this is a representation of the quad trees, the nodes of level 2 that comprise this. But we also have a future that we can represent, which is this, the center of this. So let's compute it real quick. What happens in the future for all these guys? So I'm just going to... Okay. Well, we don't know about the border, right? Because their neighbors are outside of this 4x4. But we can answer this question for the central two cells. So this cell has... What's Conway's life? The rules. I just need to quickly brush up on the rules. Sorry. Oh boy, this is embarrassing. Conway's life rules. That's a video or something. Thank you, Wikipedia. Rules. Okay. Any live cell with fewer than... Okay, any live cell with 2 or 3 live neighbors lives on to the next generation. So this one is a live cell up here with 3 live neighbors. So it lives on. Let's find out for this one. So it's dead, but it has 1, 2, 3, 4, 5 live neighbors. So a dead cell with exactly 3 becomes a live cell. Oh, these are easier. Any dead cell with 3 ones. Okay. So this one stays dead because it doesn't have exactly 3 neighbors. This one down here, it's alive and it has 2, so it stays alive. And this one is alive and it has 2, so it stays alive. So these are the future states of these cells. It happens to be no different from before. But because it's in the center, or rather because it stays the same like this, so what we would do, 1, 0, 1, 1. So we're done simulating. So the future of this XOXX is E. So in other words, that was a lot of manual work, but basically, in other words, the level 3 node XOLH has a central future of E. So that's pretty neat, but sadly, the work of finding out... Oh, sorry. So, right, every 4x4 grid, every level 3 node can store the level 2 future of its center. There we go. But higher level nodes can store... Sorry. This can be generalized to any node. And a level n node can store the level n-1 future of its center. However, nodes of a level greater than 3 have to stitch together the futures of their child nodes. In other words, well, I'm going to just point at some of these images. Here we go. So this is a level 4 node, right? And its children are level 3. And they have level 2 futures in their centers, right? To get the central future of the level 4, which is a level 3 node, we can borrow these parts of the level 3, which look meager, I admit. However, it's 1/4 of the work, right? So sometimes that's quite useful. What the HashLife algorithm does is it actually reconstructs, the rest of that center so that you can compute it. It fills in this central, right, so I should say that. I do that. I do say that. So stitching together is a central part of this. But once you can stitch these things together, the caching you do is, what would you call it? Is multi-level, right? Like this, according to one of Gosper's biggest fans, who presented HashLife in a 6-minute talk that does not cover the details, understandably. The speed up that we would get from this is considerable. But the special sauce, the magic of HashLife, is the super speed, which is basically this. And this is wild. I'm not going to try to illustrate it in text. But basically, the future stored in the center of this 4x4 doesn't have to be the immediate future, one time step in the future. It can be 2 to the n steps in the future, where n is the level of the node. So a level 4 node, I think, can store 2 steps in the future rather than 1, and a level 8 node can store 4 steps in the future, and a level 4 node can store 8 in the future, and a level 5 can store 16 in the future, something like that. The level, with a clever twist to the algorithm, a level n node can store its central future at 2 to the n minus m steps. I forget what m is, but it's constant. I should make it a constant. N minus c. I forget what c is. You get what I'm saying? So the reason... Whoa. The reason Golly can simulate so fast, right? So it's at generation 100,000, 200,000, 300,000, 1 million, 2 million, 4 million, 8 million. The reason this is possible is because the steps are accelerating. You see, it went from 8 to the 6th to 8 to the 7th. And then it'll do 8 to the 8th. Now this is cool and all, but just to be clear, this is still a stress test of HashLife. The Golly program supports something like HashLife, like super speed, right? For Wireworld as well. And remember, Wireworld behaves quite nicely, I think, because basically it never escapes its boundary. The size of the simulation, like the spatial size, never changes. The configuration changes. changes all the time. But every configuration changes. The future is always different from the past, right? Unless you have like what are they called? A cycle, a clock, or whatever they're called. A looping pattern. So when we run a Wireworld simulation in Gali, we're at 8 to the 4, 8 to the 5, 8 to the 6th, staying at 8 to the 6th, 8 to the 7th, but look at this. 83, 89, 97, 101, 103. It's entirely possible that the program to find prime numbers represented in this simulated Wireworld computer is entirely possible that based on the speed of the HashLife algorithm, it will skip some results, right? Because the cached future of this simulation might not need to represent, you know what I'm saying? Like, it's pretty impressive. 211, 223, 229. I'm going to stop it there, because it's at 220 million generations right now. Which, you may notice, this is running slower than the HashLife that was doing Conway's Game of Life. And one of the reasons for that is because Conway's Game of Life, however, Conway's Game of Life has fewer states, has 2 states, and simpler rules than Wireworld. So there are clever programming tricks it can leverage that perhaps we cannot, right? Because these states, these 2 states, correspond with zeros and ones, so that a single bit in a number could represent a single cell, right? This is my current understanding of HashLife. Now, Gali's source code is open source, but I'm not 100% sure whether HashLife is actually written to support Wireworld. It's also written in a different language than, you know, the one that we're using. But there is a HashLife implementation that someone named Copy produced. It is licensed under BSD. Let's see. Redistribution of source code must retain the above. Right. Redistributions in binary form must produce. So here's what I'm going to do. I'm not going to do clean room, right? But I'm not going to copy this stuff either. During the stream, I'm going to read this JavaScript and take notes. But before I do that, I'm going to read a few other explanations, including this original one, right? This is one that I read years ago to get this far. I'm going to reread it to better understand. Oh, but it's 7 pages. Is it? Maybe not. One moment. If I do print, what happens? I see. That is the entire article. Although, I will keep it in this format, just because this is simpler. And in black and white. Thanks, Dr. Dobbs, whoever that is. Hope you haven't been problematic since 2006. Now, there's someone named, well, Jenny Owens, who, Owen. Sorry, hang on. Because the Wireworld computer is made by a Sorry, 1 second. Right, Mark Owen is one of the collaborators of the Wireworld computer. I wonder if Jenny Owen is at all related to Mark Owen. That is, you know what? That is a question I will answer off stream because it's none of your business and it's none of my business, but I can still find out, and I think it would be interesting to know. But, you know, I'm not going to venture into that uncomfortable territory on stream. Anyway, just going to read this real quick. It would be cool to read Jenny Owen's master's dissertation. Oh, wait. So that's the original paper, and then this one. You know what? I'll look this up in my free time as well. But I will read Jenny Owen's website. Gosper's algorithm. Okay. Hashing 2D cellular automata like ours. If she can be contacted, I will also thank her after the stream. That's good positive feedback. I see. This is, okay, so this is the section of her dissertation that's online. Fantastic. Unfortunate students. I guess I have made myself an unfortunate student. And don't want to spend the best part of a week stumbling through the original paper. You can stumble through this as well. Thank you. It is highly efficient when compared with other simulators because it uses hashing and a mechanism Gosper named macrocells. That's what this is. The special sauce. No, these stitching things together, different nodes. Hashing. Actually, I'll be right back. Gonna quit Gosper. Almost full charge on the battery. I'll be right back. I'm just going to hydrate because I'm caffeinating, but caffeinated soda does not exactly hydrate as well as water. Well, thanks for waiting. I left to get some water, and I did get water. What else did I get? Half a bacon grilled cheese. Life is good. It's stressful. It's complicated sometimes, but it's good. Sorry, one moment. I need to blow my nose. Right. Where were we? Hash table. JavaScript hash tables are built in, but we might implement our own. She's making a big deal of the key in the hash table being generated from other data, which for a lower level implementation makes perfect sense. I wonder how that will transfer over to a JavaScript implementation. I should write that down. Notes from Jenny has a hat. Research. Okay. Right. So, the method of hashing is significant. How will we look up what will we use as key values, as keys in our hash table? Right. Do macrocells not directly reference their futures? Are the futures just stored in the hash table, keyed by their pasts? A macrocell is a... okay, enough speculation. A macrocell is a square of cellular... right. So, terminology, macrocell. We are going to adopt that terminology. Yes. Oh, it does point to 5. Okay. So that's not true. This might be true. Okay. Northwest, northeast, southwest, southeast, and central future. That's the 5 smaller 2 and I think 4 of these are the 4 quarters of the right. 1, 2, 3, 4. The other cell is what Gosper refers to as the result. Okay. Result. AKA central future. Okay. It contains the state of the macrocell after 2 to the n minus 2 steps. Okay, so up here, we can change that C in here. C equals 2. Here, you know what? I'll just put it in n minus 2. Okay. 2 to the caret n minus 2 future. Central future. And it is entirely determined by the state of the macrocell. That is an important insight. You can always, always, always compute this from what's out here. In a worst case scenario, you write all of these cells out, simulate it, and store it. The reason the result is that size is that it will take that number of time steps for information outside the macrocell to penetrate the result cell's border. Yep. All of these neighbor relationships have a kind of Einstein relativistic light cone where this future is impacted by this past for any scale. And because we're talking about larger scales of space, we're talking about deeper scales of time. The result square is the only information that can be accurately predicted. Yes. So true, so true. The important thing to note is that they are recursive. Yes. I'm not going to shy away from recursion. Right. Which of course, so these are the X's and O's we were fooling around with. Each macrocell can also be reused. If a macrocell is a repeat of a previously discovered one, then it will behave in exactly the same way. That's what they're for. The hash table contains all macrocells when that's what it is. So anytime you have to stitch together the future, you can then convert that data into a key into the hash table in case that state's future is already represented. Got it. I wonder if the hash table stores all macrocells regardless of level, or if there's a different hash table for each level. That might be implementation specific. When a macrocell is 4x4 in size, it is easy to calculate the result using brute force. Okay. At some level, the result is trivial to brute force. The cell only needs to advance one time step. That makes sense. However, problems arise when n is greater than 2. Yep. If we take the... Right. We see the results from the quadrants do not fill the area required. Furthermore, these results are from 2 to the n minus 3 time steps into the future and not 2 to the n minus 2, because the existing results are from the quadrant cells of size 2 to the n minus 1. And so the result is at time 2 to the n minus 2 minus 1, or 2 to the n minus 3. Right. So actually, these 4 corners aren't 1/16 of the result. They are, let's see, they are 1/36 of the past of the result. The solution Gosper proposed is scalable for all values of n. We will explain it here using an example at n equals 3. For some reason, this is easier to focus on than the Dobbs article, though I haven't tried reading this in a long time. The first step, okay, Gosper's algorithm in English, in simple terms. Right. Compute the future at the time step of the children's computed futures. So that gives you the corners, and then you have to do these ones. So this is the stitching. I'm going to call it Gosperize. Gosperify? Gosperize. Just for now. Right, so this future, this future, this future, this future. Great. Oh, and we can, right, we can use more of them. So actually, it's not as bad as I thought. These 4 futures we can immediately apply, and that gives us one, two, three, four, 4 out of 9. Not 4 out of 9. What am I saying? Oh, no, yeah, 4 out of 9, because it's divisible by 3. Okay. I gotta focus. Okay. The remaining area is calculated by making 5 temporary... Okay. The corners are already solved. The 5 unsolved missing bits are made by temporarily constructing 5 macrocells. The remaining area is calculated by making 5 temporary macrocells. But how do you make a macrocell? Ah, we've got their present. Oh, it's a 4x4, not small macro. Yeah, small macrocells. You know, whoops. You know their present, Gosperize their future. And that lets you stitch those. And then we need to reduce the 6x6 into a 4x4. By creating 4 more temporaries. Temporary. Right. Then make 4 the result is a middle ground future. Make 4 more unsolved, missing make 4 more temporary macrocells from the middle ground and solve them and Gosperize them. Anytime you Gosperize, though, look up or Gosperize, you start by looking up if the result is already known, I guess? I suppose? And that gives you the result. That gives you a properly sized, properly timed result. Do the temporary macrocells get thrown away? What scheme is used to prune the cache, the hash table? Okay. The overall result... Right, sorry. With larger... Okay. The overall result of the algorithm is to consume much less memory than a naive alternative, absolutely, through recycling of macrocells. Let's see. Yeah, this is nice. The macrocells are also able to predict their state 2 to the n minus 2 steps into the future, and if n is large, this also results in a significant loss of overhead. HashLife performs best for repetitive or periodic patterns, like Wireworld. I mean, it's not 100% repetitive, but no pattern is 100%. I mean, you never feed HashLife a 100% repetitive pattern. You're interested in the ones that are not fully aperiodic. For more chaotic patterns, the algorithm is less efficient as macrocells are less likely to be repeated. Right. Sorry, 1 second. Sorry for the wait. Life does not sit still for a live stream, does it? But it's all good. Right, so this is... Jenny has a hat, I don't have a hat, but if I had a hat, hats off to Jenny who has a hat, because this really boosts my confidence in my ability to implement this. It doesn't seem so difficult because of this explanation, really. I'm sure we're going to encounter some real serious bugs, but I'm more amped than ever to try this. Okay. Also, it really helps that the explanation that Jenny Owen provides doesn't go through the incremental steps that the YouTube video I had previously watched recommends, where you put everything in macrocells and only model the immediate future in every macrocell rather than the full time step. It is interesting that at some point the time step will have to be adjustable. So to adjust the time step, do you create a higher versus lower level quad tree? In other words, technically, Wireworld right now has macrocells of size 1. They're not very good, right? But if they were good, and I made the step size 2 to the 1, then it would run the exact same way as it currently does. But if I made it 2 to the 2 or 2 to the 3, little quad trees adjacent to each other would occupy the entire simulation. And each of them would share the cache and would simulate at that level. And then as I increase the time step, I would join those nodes together into macrocells of a higher level. I think that's the way forward. Understandably, that detail, which really caters to the user rather than the advancing of the simulation, right, academically, is not in Jenny Owen's explanation, which is fine. I mean, of course. You know, the speed slider and zoom slider aren't in any of these either, for obvious reasons. It's just something that I'll keep in the back of my mind, because at some point I will want to implement the time step, ramp up, ramp down functionality. And it's been implemented. It's been implemented in Gosper, in Golly, and it's been implemented in Copy's Life. What is Copy's name? Sorry, one second. Fabian. I will also reach out and thank Fabian. But again, I am not going to take anything from Fabian's HashLife implementation. Not to mention the fact that the code Fabian wrote to do HashLife presumably is specific to Conway's Game of Life, which is a different rule set than the one that I'm working with. But I have no motivation to cheat or steal. Geez. Sorry, Dr. Dobbs, whoever wrote this. Who did write this? The author is not listed. But honestly, my eyes are glazing over reading this. And me getting bored is not fun to watch on Twitch. Here, 1 second. Right. Oh, my first improvement to the base. It's Gosper. This is an article Gosper must have written. Okay. Good algorithm, Gosper. Also, I'm glad you're keeping the spirit of Martin Gardner alive. Right, quad tree. Nothing new yet. You know what? I'm gonna skim past this. I'm gonna look at the code in here. Class node, next generation. If level is 2, do base. Right, so this is the trivial calculation. Otherwise, new node. Oh, that's handy. Okay. Why a simple recursive algorithm? Right. Yep. I construct 9 new nodes. So the 9 new nodes that Gosper computes are... So remember, this red box, this red box, this red box, and this red box are the futures of the child nodes. But this red box, and this one, and this one, and this one, and this one, they need to be they need to be temporarily constructed, and they generate this 6x6. Sorry, they generate this 6x6. And then 1, 2, 3, 4 generates the 4x4. Okay. Node is a function centered subnode. Return new node. Right. Center horizontal. Oh, I see. Oh, clever. Okay. So these, so notes from Gosper. Notes from Gosper's Dr. Dobbs article. Create utility functions to generate the temporary macrocells from the child macrocells of the child. Okay. That's hard to parse. But basically, this code, so these are utility functions that generate this node, and where does it get its pieces from? From the existing child nodes. That makes perfect sense. I hadn't thought that far. Node next generation, if levels 2, do the base, right? Else, okay, so this was temporary. Oh, this is the thing that doesn't work. I see. Right. Right. Okay. So instead of that, it's this. You generate the 9 extra nodes, and then you calculate them. Got it. Huh. Ah. I was expecting more next generations. This is the increment that the YouTube presenter was talking about. So this allows you to reconstruct a central node and call next generation. But by doing next generation on these buddies, you get... Right, immutable bitmap. I can't do bitmap. I can do nibble map. Bit means on and off, and I've got dead wire cell head. So there's no need to have distinct nodes that share the same value. Right, okay. Right, by itself this is in Java, so it's not Gosper from, let's call it pseudo Gosper, because it's somebody who I thought was Gosper and speaks as someone who's implemented this already, but this was someone who, you know what, let me just pull up the actual credits for this article. Who wrote this? Oh, okay, this is the person who presented that YouTube video. Okay, not pseudo Gosper. Okay, yes. Cool. Provenance. So, yep. Canonical tree node. Applying canonicalization with a cache to improving the performance of a Fibonacci algorithm. Okay, recursive formulation. Add a single pointer to the node data structure that stores the result, right? If the pointer is not null, contains it. The speed up attained through memorization that was enabled by keeping next generation partly functional more than offsets the inefficiency introduced by returning a nodal level down from its argument. Good. At this point, it's not quite HashLife yet, correct. We're incrementally closer, though. On some large universes with regular patterns, it is faster. Blah, blah, blah. Compression of time. Compression of time. Indent. Right. The number of generations the recursive call computes. Horizontal forward, you grab the next generation. Next generation. Next generation. Grab the next generation of the child nodes, and then you combine them again, next generation. That is HashLife. Okay. I am feeling it. Okay. Yeah. This exponential computation, this runaway simulation is what I'm really working toward. Let me return to the beginning. In December 2000, on a private mailing list, Nick Gotts posed a new and wonderful 52-cell pattern called metacatachrist. Golly. Patterns, HashLife, metacatachrist. View fit pattern. Not much, right? It's probably going to create some glider guns, which is the name of one of the types of things that construct themselves in Conway's Game of Life. Okay, 8 to the 1, 8 to the 2, 8 to the 3, 4, 5, 6, 7, 8 to the 8, 8 to the 9, 8 to the 10. And if you look at this, I mean, look at this. This density. What is all this? You zoom in, and it's tons of Just zigzagging cubes, boxes. I don't know what they're called. Um, let's see how they're constructed. Let's go up here to the edge of one of them. Oh, interesting. These cubes aren't made one by one, but the process that makes them... Oops, the time step is still too high. Slower. Oh, that's funny. This UI is the same UI that the life simulation that Fabian, aka Copy, made uses. So slow down the time step to 1. Drag. 2. Zoom out. 3. Zoom out. 4. There they are in formation. 5. Incredible. 6. 7. Excuse me. Excuse me. 8. And then boom, it reached the edge. Is there anything going on at the edge down here? Probably not. Just curious. Nope. That's funny though. This little guy. Oh. Hello. Okay. So, quite impressive considering how simple the starting conditions are. Just a couple of these and a couple of those at the right distances to each other. Gonna blow my nose. 1 second. I have returned. Okay, so Metacatachrist. Nick Gotts was confident it exhibited quadratic growth, but was not absolutely certain. Sorry, coughing, 1 second. And back. He asked if anyone could run a HashLife against it, having just finished a fast conventional life program, and having seen enough hints and rumors about how such program might work. And since Bill Gosper's original implementation only worked on Lisp machines, of which there were few, fair enough, I thought it was time to try to write one. With my embryonic incorporation of the ideas I've presented so far, I was able to run Metacatachrist to many trillions of generations and show that it exhibited quadratic growth throughout the range. This pattern is amazingly beautiful with fractal properties that cannot be appreciated without running it for billions of generations, and having the ability to display the resulting universe in some sufficiently scaled, zoomable form. We're well past the billions now. Okay. Awesome. Download the source code that accompanies the article. Sure. It's in Java. That's not so bad if I want to actually look at it. README. That's interesting. He's left some suggestions on things to explore. Also, whole nother website. Not found. Well, it existed at some point. Hello? I see. I think I'm going to link to all of these sites in the description of of this episode when I upload it, after I upload the last episode. Right, so this, by the way, is what Fabian's simulator looks like. And it's going to accelerate the time step. No? I'll do it. And it's specified down here. Fit. Speed up, speed up, speed up, speed up. This is all JavaScript based, so I should be able to learn something from looking at its code without writing any code of my own. I should look that up. Can I... Okay. Independent creation. I see. I cannot implement a clean room implementation of this because I'm the person who will be looking at this code anyway. Do I... Do I want to do that? Just gonna back away slowly from that. Okay. I will still link to it in the description, but I am not going to do that at all. Okay. I'm not looking at Fabian, aka copies. Or Rokicki's, actually. To do. HashLife. You've got what it takes to implement this all by yourself with the knowledge taught by others, but not by looking at their code. Okay. HashLife. Okay. Uploading notes. Oops. Then what? I will copy paste excuse me, naive. And this one is going to be called hash. Is it? What's a better name? Macrocell. So cool. Engine common. Let's pick a color scheme we haven't used yet. We're going to use current, I think. Oops. Wireworld JS. Oh, the default is going to be macrocell. Excuse me. I'm at the end of a cold. I'm sorry. I'm in that gross phase. I just need to, like, physically get rid of it. Okay, macrocell, and then an index. Option class equals macrocell. Value equals macrocell. Selected. Macrocell. That works. That works. That works. That doesn't work. What is going on? Wireworld. Macrocell. Oh, here we go. There it is. It looks... It looks cool. I hope it looks cool on the stream. But yeah, obviously this is not the true... So right now... Okay, so... Getting ahead of myself. prettier. Everything's fine. Creating macrocell engine that has a copy of naive implementation. Adding macrocell engine option to the GUI and setting the default option engine to macrocell. Default engine should be specified in Wireworld module transmitted to GUI. Let's just append that. Okay. Oh, that's weird. Old themes. Ugh. Let me just get rid of this real quick. Some code that doesn't need to be there. Okay. Little bit of code cleanup. It's actually much nicer to look at when zoomed in. That's one of the downsides aesthetically to Wireworld. It's wiry, so you don't get to really appreciate the colors of any color theme unless the electrons are always bright and the wire color is always low contrast with the background. I'm getting distracted. Okay. HashLife notes. Macro cell. Old cells, new cells. We don't need that. We don't need that. We should probably store width and height. Cell IDs by grid index is a good idea. We will not worry about save data until later. To do, implement reset. To do, restore from support, restore from save data. Update. To do, for every cell, yada yada yada. Bloop. We might actually need to support a different rendering solution for this. Maybe. It just might make more sense to send a bitmap instead of this. To do. Maybe send a bitmap to the renderer. A bitmap of the head, tail cells to the renderer. Okay. And this just creates the cell IDs by grid index, which actually we don't need because we're probably not going. Excuse me. Oh, I see. Yeah. Gross. Oh boy. So, because we rely on render for the head IDs and tail IDs, yeah, we still need to send the cell grid indices. Okay, I'm not going to worry about that right now. I'm going to do this. Return empty array. Nice. To do. We still have this useful post-debug utility function in the engines that will allow me to basically console log everything. So, for example, there are all the cells. Yep, great. I should start with a way, okay, to do. Gotta plan this. So, initialize HashLife from data. That's step one. Post debug. Two, alternative render solution. Save restore from bitmap if it's present. There you go. Three. Implement Gosper's algo in bitmap function. No. Implement macrocell utility methods. Nope, that's 1, 2, 3. Implement update function. Input time step. Connect with turbo, or no? And then 6, implement reset from head IDs, tail IDs. Create a bitmap. Rasterize, really. Rasterize. Well, yeah. And then read into initialize macrocells from rasterized result instead of initial rasterization. Of initial data. Okay, rasterize into map into matrix of cell state. That's how we do it. In reset, we initialize the HashLife from data in reset. So actually, initialize doesn't do anything. Not really. Reset is where we throw away the, well, empty the cache, build, build quad, well, build macro cells from save data or from initial data. Okay, so just like engine common holds on to original data, macro cell will also original data equals data, or from original data. Rasterize, save data into matrix of cell state. Okay, so that makes these basically the same. So reset from head IDs, tail IDs is no longer necessary. Okay. So far, so good. let cache equal new map. Const cache equals new map. MDN map clear? Is that? Yes. So cache dot clear. If save data isn't null, const okay, const raster equals rasterize const cell states equals save data is null, original data dot cell states, otherwise recover two cell states. Get cell states save data. That's what it is. Okay. Const get cell states if save data is null, return original data dot cell states. Const cell states equals array height dot fill dot map array dot width array width dot fill cell state dot cell states equals original data dot cell states dot map row dot map state equals cell state dot dead cell state dot dead okay. For let y equals 0, y is less than height, y plus plus. For x is less than x equals 0, x is less than width, x plus plus. I don't like this either. Const, okay, const cell states equals, I'm just going to make a 2D array real quick. Array height dot fill dot map array width dot fill cell state dot dead. For let y equals 0, y is less than height, y plus plus. For let x equals 0, x is less than height, width, x plus plus. Okay, So now we have every y and every x. Const index equals y times width plus x. I'm getting ahead of myself because save data is going to have a value in it that, okay, I'm just going to hold off on this for now. To do, return cell states. And then we rasterize it into a matrix of cell state. Right, that's what this is going to be. Transfer save data into cell states. Build macrocells from save data or from original data. Const, one second, let width, height, largest, pow, to, smallest, let's just call it size. So width and height, cool. Size equals, let's see, const largest length equals math dot max width height. Size equals 1, while size is less than largest length. Size gets twice as big. There's probably a better way to do this. Hang on. It's like math.log? Base 2? This is fine. This is readable. We're also going to add let times sim, what would you call it? What does Golly call it? Step pow equals 1. To do, no, step pow is 1 is fine for now. So then sorry, that gets added to the to-do. Reset the, well, grow or shrink the simulation. Okay. Step pow is 1. It's recursive, so this building of macrocells needs to be recursive as well. Build macrocells, step pow, cell states. No, I create the bottommost layer first. How am I representing this? Because this is where the macrocells need to go into a grid, but the grid needs to be remade for every layer? Yeah. For let I equals 0, I is less than step pow I plus plus, const. Macrocells equals array step pow. Dot fill dot map array. This is annoying. Do I seriously have to create a grid of macrocells for every step that I'm simulating just to generate them? You know what? Forget this. It's not that we make a bunch of grids. That is a quad tree. So we're going to say no, I need to think this through still. Const cache. Let's step pow is 1, top cell equals null. Okay, here we go. Top cell equals, and now here's a recursive function, generate reset macro cell, cell states, zero, zero. Here, cell states, step pow. Ah, no, it's size. Yep, size. Zero, zero. Okay. And now I need to make this. Cool. Okay. Const reset macro cell. Make macro cell. load macrocell, cell states, size, x offset, y offset. Okay. If size is equal to 1, is equal to 2. Okay, so cache's new map, const base cells equals new set call these leaves. Leaves. Let's see. Okay. Const make macro cell. What's make cell? Okay. Make macro cell equals. And it's like leaf const make cell equals northeast, northwest, southeast, southwest result. Northeast, northwest, southeast, southwest result. Make leaf is state So leaves is make leaf cell state dot dead wire tail head. Clear the cache, and then we immediately say cache dot add leaves dot for each leaf cache dot set shoot. We need to memoize. Well, I'm learning a lot. We can't put anything in the cache until we have a way to map the cache to like a key. We need to memoize it. Which, for Conway's Game of Life, is just a long bit field, I guess? No, it's not. It needs to be a GUID for this is where I got stuck 10 years ago, because I did try this 10 years ago in Wireworld AS3. Source, net, res mason, Wireworld, brains. Or maybe I got rid of it. Probably did. Hex model, hex classes, net, res mason, Wireworld. Tree model, and tree calc scope, and tree node. I think I need to start simpler. Start simple. Build simulations from nothing. Here. Figure out how to memoize a macro cell. Because it can't just be a hash of the actual state. It can't just be a hash of the actual state of the cell. It's got to be based on the IDs of its children. But those IDs are memoized. Ah, okay. When you create the smallest macro cells, they populate the okay, so convert here, I'm gonna top cell. It's like I'm trying to fight for a good vantage point for actually writing the thing. I could build it up from the bottom, convert a grid of cells into a macro cell. That's the first thing that I should do. Doesn't matter how just yet. Just do it. Okay. That's where I'm going to start. Represent cells in a quad tree. So actually, there is some merit to building this conceptually from simpler ideas. So I know how to make a quad tree. I mean, it's not even a hard quad tree. There is a definite leaf at the 1x1 pixel level, the 1x1 cell level for a macro cell. And there's definitely like a 4x4 thing going on for the 2x2. And there's a 4x4, sorry, there's 4 cells in the 8x8 and 4 cells in the 16x16, etc. So, Doesn't matter how. Yep, okay, so once I get the cells in a quad tree, modify the quad tree to look for, to search for, I think, to search for northwest, northeast, southwest, southeast in the cache. If it doesn't exist, create it. ID++. So everything is gonna, every macrocell is gonna have its own ID. Make it a string, actually. String GUID. It doesn't matter what the value is as long as it's unique. Right? I don't know. Modify the quad tree to search for an existing parent of its children in the cache. If it doesn't exist, create it. Return it. Okay. I'm going to reset macrocell entirely. So it's back to being the naive implementation. But up here, I'm going to say const cache equals new map. Const leaves equals just as before. You know what? Cell state. Cell state is a thing. It's got properties. Yep. Object dot values dot map object dot from entries object dot entries cell state dot map name value name we're going to call that state. Okay. Whoa. Post debug leaves. Head, tail, wire, dead. Okay. MDN map add. Map set. Ah, the leaves don't go in the cache. Okay, the leaves don't go in the cache. Yeah, this is fine. Base MC template, macro cell template. Const macro cell template equals northwest null, northeast null, southwest null, southeast null, result null. Post debug leaves. All right. State null. Now the reason I'm doing this is I kind of want the leaves and the cells to have the same footprint. Like all this is unnecessary for the leaves, but if they have the same shape, then JavaScript might optimize them so that they can occupy the same value on one another. Okay. I think I can do this. All right. Gonna do... You know what? Yeah, this is a distraction, so gonna get rid of these. Size. This is gonna be called tree height. Okay. Get rid of this. Or rather, original cells equals data dot cell states. Do I care? Yes. Yep. And in here, return that. Reset. We're just going to do that. To do, update, to do, render, to do. Rendering and saving and restoring are going to be like the last things we figure out, actually. Okay, this ought to run still. And it does. Okay. So we've got original cells, and now we can mess around with it. Size equals 1, while size const max dimension equals math.max width height. That's a better name. While size is it size or tree height? Hang on. It's both size, tree height. Size is 1, tree height equals 1. While size is less than max dimension. Size times equals 2. Tree height gets incremented by 1. Post debug, size tree height. 1024, 11. That makes sense. Width, height, or max dimension. Okay, yeah, 800 is larger than 512, so we need to go up to 1024. That's fine. Okay. And now we need to make a recursive function, which is top cell equals make cell we're going to call it init cell. Original cells. Right. Const cell states equals okay, cells. Tree height. Yeah. Tree height and 0, 0. Okay, we're going to try this again. To const init cell equals cell, cells height x, y. Okay. And this is going to return first of all, we're going to make sure we've got the macrocell template represented, and then macro cell template, northwest init cell, cells height -1, x minus bump, y minus bump, northeast, southwest, southeast, result null. Ah, hang on. Const northwest equals. Nope. If height is equal to 1, then we do one thing. Otherwise, const northwest equals init cell, cells height -1, x minus bump, y minus bump, northeast, southwest, southeast, northeast is x plus bump, plus bump, plus bump for south, plus bump. Okay. If cache dot has northwest dot ID, right, these need an ID, ID null. Northwest, northeast, southwest, southeast. If it has it, const existing cell equals, and this is the ID, const ID equals that. If existing cell is null, return existing cell. Let's turn this around. Okay. If cache.hasId is false, then const cell equals, and here's where we actually make the cell. Macro cell template, northwest, northeast, southwest, southeast. Result? Maybe? I'm not going to worry about result for now. And I don't care about state, but I do care about the ID. ID. Okay, cool. Cache dot set ID cell. Return cache dot get ID. Boom. Okay. This is gross, because it just concatenates the IDs, doesn't it? That's not it. This is the key. ID, IDs plus plus. Set key. Might as well do this. Oh no, we don't need the. Okay, cool. Right. ID, 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 ID. Cache has key. There is no connection between the key and the cell other than the mapping in the cache. Cool. Okay. That keeps us from doing this concatenation garbage, which would literally map to the recursive quad tree of stuff. That was a close call. That was almost stupid. Okay. Init cell IDs equals 0. Let's find top cell. Top cell doesn't exist. Let top cell equal null. Let IDs equal 0. Okay. This works. We need to handle the leaves, but northwest, northeast, southwest. 1 second. Return cache dot get key. Okay. If height is 1, oh, we also need to make bump. So here, const bump equals 2 to the height minus 1, I think? Let me think. If this is a 2 by 2, then let's just try that. If height is 1, return leaves cells y x. Is it that straightforward? Leaves is an object where we're mapping, so this is cell states to leaves. We could just do new map. because that should be a cell state. Height -1. Const lower equals height -1. Does this work? Init cell is recursive, top cell, post debug, top cell. Evaluating cells YX failed. Post debug, cells Y, cells Y. Let's just do XY. I see, that's why. Okay. So instead of that, init cell, this should be size over 2, size over 2. Maybe 0? No. -1. Post debug height XY. Okay, so 512, 512, and then minus. Huh. So it should start at 512 by 512, and then we're subtracting way too much. Height -2? This is, it gets too small here. Also, yeah, okay. So, -2 is correct. That's so strange though. 512 minus 512, height -2, x minus bump, x plus bump. 2? Should probably be size over 2 -1, huh? Yes. Okay. Const center equals size over 2 -1. Okay, so then if height equals 2, height xy. Height equals 1. Nope. Huh. I see. So it shouldn't be minus bump plus bump. It should be like 0, 1 should be the... Okay. This should be 0, 0. And then... like that. This looks good. So then... Tree height minus 1. I don't know the math off the top of my head, but I can tweak that and then actually think through it. But first I'm curious what this is. Undefined is not an object. nw.id. Oh, that's why. Okay. So... state ID state. Minus state. ID is null. And ID here is state. And ID here is IDs plus plus. So everything should have an ID. Console, post debug, NW, NE, SW, SE, ID. Undefined for all of them. So init cell right. It's looking in here by the key. No, this should be working. So state also undefined. Well, it's not looking in the cache for it. Const leaf equals cell states to leaves. Return leaf. Product post debug leaf leaf is not equal to null. They are null. Cells y x. That's why. Okay. These aren't cell states to leaves, these are the names of cell states. Okay, we don't need that at all. We need object.values cell state dot map state. Let's try that. Cell states to leaves. Dot has that. False. Post debug. Cell states to leaves. You jerk. Here we go. Okay. Object.values. Cell states to leaves. Cell state. 0, 1, 2, and 3. Good. Dot map state to... Ah, that's why. State. There we go. Oh, that's a lot. That's a lot. Let's get rid of that. Okay. Let's get rid of these post debugs. And try that again. Am I posting top cell? I am. Okay. Holy smoke. Okay. All right. All right, we got this. We got this. Just drilling down. There it is. All right. I know it doesn't look like much, but this is a big old quad tree, right? And in the quad tree, there are these relationships that result in these leaves. We just made cells in a quad tree that are cached. Quad tree of cached nodes. Check. Anytime you make a new cell, you have to create its future. Right? I think. That's the next question. This future stuff. At least we've got the quad tree. So maybe, quad tree of cached nodes, check. Anytime you make a new cell, you have to create its future. That is the tricky thing. I may actually need to go up a cell. Or up a level in the quad tree, so that the light cone of the macro cell at the top contains the entire thing. But something else I could work on in the meantime is render to screen. New rendering system based on bitmaps. Bitmap can also be used for recovery. For save file instead of head IDs and tail IDs. It would be worth considering. So what's nice about macrocells is they don't know where they are. They only know what they're made of, and they know their future, eventually. So anytime we need to draw anything, we need to do the same recursion that we just did in init cell, where we get the x and the y, and we pass it into itself to render. This recursive structure is probably going to crop up again. I mean, how else do we draw it, right? Gonna rename this offset. Height -3, height -1. Child height. I gotta say, the fact that I even have a quad tree makes me feel great. Prettify. What changed? Macrocell template got expanded, and cell states to leaves got turned into a single line. That's fine. Right? Yeah, this is fine. I'm going to rename this to cell template though. Cell template. Yep. I wonder, tricky relationship, so how does clearing the, how is the cache pruned or cleared? If it's pruned, how are new IDs, new GUIDs decided on? How are GUIDs impacted? Because there's an int max to worry about. How many cells do I currently have? Should be easy to find out. IDs, post, debug, IDs, top cell. Our quad tree contains 4,033 unique cells. That's actually not that much, but it only represents an instant in time. We have not yet populated the cache with the future, and yeah, I guess the future, I guess the update function is going to replace top cell with its future. And it's going to make that new top cell from a recursive function. Jeez Louise. Alright. It's 10 p.m. Pacific. The sun has set over the skybox in the corner of the level. I'm excited. I'm also parched. Soon after I'm done here, I will upload last week's episode and this week's episode, and I'm going to put these fine folks, the links to their things. What was it? GitHub, copy life. I'll put links to these 4 things in the description this time. Oh, I need to finish, okay. So, the quad tree composed of cached nodes is implemented. Pretty exciting. And I'm going to tag it. Tag episode 11. And push. Well, thank you for joining me tonight. I'm excited for the next episode.